Hello everyone, hope you all are fine. Today we will deal with the stress-strain curve of a loaded material. So what is the significance of this stress-strain curve? We have to understand that in our daily life there are a lot of materials which we term as ductile, malleable, elastomer, brittle, like that. So for that, in order to analyze which material can be used in which application, we have to go into the detail of this stress-strain curve. So this is the stress-strain curve of a loaded material where stress is plotted on the y-axis and strain is plotted on the x-axis. Now, we will study about the region OA. What do you see in this region? It's a straight line. So, if it's a straight line, what does it mean? When we increase the stress, the strain is proportional to stress. Whatever stress is applied, stress is proportional, directly proportional to strain. That's why we will get a straight region till OA. So, till A, when the stress is increased, the proportional relation between the stress and the strain is maintained. So, the point A is called the proportional limit. After this point A, when we increase the stress, look, for a small increase in stress, the strain produced is more. It is not that much proportional. There is a slight bend in the curve. But this point B is called elastic limit or yielding point. What does it mean, elastic limit? That means that when we apply a deforming force on a body, stress should be proportional to strain. Till B, when the deforming forces are removed, the body will come back to its original position. It can regain its original position. But beyond the elastic limit, it is not so. Look at the region between B and C. When we increase the stress further, what happens is that for a very small increase in stress, the strain is huge and the material gets deformed in such a way that it cannot regain its original size. So listen, here moving from B to C. At C, while we try to unload this material or we reduce the stress to zero, we expect that this will come back to its original position. But at C, it is not like that. When we are reducing the stress, gradually it will not come back to its original position as we have moved up, but it regains its original position, but there will be a residual strain inside the material, and this is what is meant by O dash. Look, whenever there is stress here, there is strain, but even if the stress has become zero, the strain hasn't reached zero. There is a permanent strain that is developed inside that material, which is called OO dash, and this OO dash is called the permanent set. So let us look beyond C. Here we know that there is not that much hike or increase in stress. A small increase in stress can produce a large strain, and this CD region, this region is called a plastic region where the material undergo plastic deformation. What do you mean by plastic deformation? Stress is not at all proportional to strain, even though a small stress can produce a large strain in the material, and from this C till it reaches D, and at D it is called the fracture point where the material breaks. So once again, taking a recap, from O to A, it's called the elastic region, or we can say that from O to B, it can be the elastic region. From O to A, it is called the proportional region, and A is called the proportional limit. And up to B, it can regain its original position. So B is called the elastic limit. Even when the deforming force is removed, it can come back to its original position. But at C, it cannot come back to its original size or shape. There is a permanent strain produced inside the material called the permanent set. From C to D, it's not at all behaving as an elastic material. It's called the plastic deformation has happened, and there's a plastic region there, and for a small stress, the strain will be very huge until the material breaks, and D is called the fracture point. The stress needed for a particular material to break is what is meant by tensile stress or breaking stress. So, for a material to break, tensile stress or breaking stress should be applied. Depending upon the stress-strain graph, let us analyze different types of materials. The first category of material is ductile material, where we can move from the elastic limit region to the fracture point. Look at this. In this ductile material, from C to D, this region is very large. It's very lengthy region between C and D. That what does it mean? We can stretch that wire and the material is ductile. So, look at the brittle materials. They are not ductile. Look, the gap between C and D points, it is very small. If it is very small, it is a brittle material. If it is large, it's a ductile material. A question can be asked to you. Two graphs will be given. Identify the brittle material. So, you have to note that the relative distance between C and D in these two graphs. If it is long, it will be a ductile material. If it is small, it will be a brittle material. Third category of materials are malleable materials. Malleable means we have to compress them. So, the graph is not like in the first quadrant. The graph is like this, compression and force. So, there is a compression, and after this, there is two regions here, A dash, B dash, like that, where A dash can be called an elastic limit and B dash can be called a crushing point. So, this is the curve of a malleable compression. Next, these elastomers. Elastomers are materials like rubber which do not obey Ohm's law. Look at this graph. It's an exponential hike. In our body, our aorta is a very good elastomer. Look, for small values of stress, the strain will be very huge, but it does not break. But these are materials which do not actually obey Hooke's law. So, once again, ductile material where the region CD is long, brittle material where the region CD is very small, then malleable material where the graph is very much different from those we have drawn, and there is a crushing point B dash, and there is an elastic limit also A dash here, and elastomers like rubber, and in our body, our aorta is a good elastomer.